Hello viewers, welcome to CAE for you. In our last video, we explored simulating high-speed impact of a bullet against a plate at various impact angles. Our successful simulation of such complicated physical process motivated us to explore OpenRadioss further. This time, we tried to simulate another complex phenomena, the detonation of TNT in air, and hence simulating the blast pressure wave during explosion. This type of simulation requires the so-called multi-material modeling. Generally, arbitrary Lagrangian Eulerian or the ALE approach is much convenient. However, Euler method is sufficient for the current case. We have chosen ALE approach so that the model can be extended to simulate fluid structure interaction cases in future. We will use Jones-Wilkins-Lee, which is referred as JWL equation of state or the UOS model for TNT. And in the same way, we will use ideal gas model for air domain. To effect explosion, the explosive has to be detonated or ignited. So in this case, instantaneous ignition model is used. Because of high pressure gradients, blast simulation will typically require high grid and time step resolutions. However, to reduce computational cost and fit within the available computational resources, 2D axisymmetric modeling was adopted, which also harnesses the geometrical and response symmetricity in this problem. Despite geometric simplification, medium spatial and time step discretization was chosen to keep modest runtime. Otherwise, these cases can take very large time for completion of simulations. This also served as an attempt to arrive at an optimal setting and understand its effect on accuracy. As usual, any simulation is meaningful only when it captures the physical process correctly. So we will compare the numerical result with the empirical result available in literature so that we can understand the validity of this methodology. Of course, this simulation provides significant insight while developing protective structures, explosive shaping and sizing for demolitions, excavations and weapon designs. Let us look into the model. As stated earlier, it is simplified 2D axisymmetric geometry representing a hemisphere in which TNT is filled for 16 cm of radius and the air domain spans to a radius of 200 cm from origin. The geometry was modeled in Gmsh. The required partition was made to enable structured grid generation. Again, structured grids are preferred for computational efficiency and accuracy. Mesh was also generated using Gmsh. Graded meshing strategy was used to have dense mesh at areas of interest. As we see in the mesh statistics, about 11,875 first order quad elements were used. The mesh is almost instantaneously generated based on the given settings. The output which we are interested is the blast pressure, which we will probe at various distance from detonation point. Sometimes it is even useful to place the nodes at the monitor points, but we didn't strictly follow in this case. We are interested to find the peak pressure up to approximately 10 times the distance of the charge radius from detonation point, which is about 150 centimeters. Since we intend to simulate open air blast, outflow boundary condition is used at suitable location. Similarly, symmetric boundary conditions were applied to account for plane symmetry. The detonation point of TNT was set to origin of the domain. Let us see the plot of pressure wavefront. Okay, we just saw the animation of pressure wave traveling due to blast of TNT. For the given inputs, that is hemispherical TNT charge of radius 15 cm, which is 150 mm with density of 1.63 gram per cubic centimeter, the charge mass is about 11.52 kilograms. As we need to find the blast wave to cross at least 150 centimeters or 1500 millimeters, we ran the simulation for 500 microseconds. We didn't pre-calculate this end time, but we just iterated it here. If you are looking forward to do this simulation, a detailed explanation about the case file with all working files are available in Gumroad for reasonable price. And the next one is the now we see that with them. Further, you can find the link in description. Moving on, we use the empirical equation to calculate the peak pressure at different locations of interest. The typical pressure plot shows the rapid rise of pressure and a decay of pressure over time, which is a blast pressure characteristics. For the probe result, we could observe the simulation captured this process well, including the negative pressure zone. Now, let us compare the peak pressures at various locations. Comparisons indicate though the relative error shows higher for radius greater than 500 mm, it is imperative that the difference is small and on conservative side. It is also important to know about the computational resources for these kind of simulations. This simulation ran for 2 core hours in a 16 GB RAM machine. This low computational head simulation makes it efficient for conceptual studies. We observe that the results are very sensitive to the location, particularly near the explosive surface. Mesh size and time step sensitivity study can be helpful if it is necessary to calculate accurate results near the TNT surface. At the same time, the numerical simulation provides reasonable and conservative results after 500 mm of radius from detonation point. We conclude that the present work can act as a good starting point for simulating blast and its related problems. Hope you liked our work. See you in our next video. Thank you for watching.